So there's not really a whole lot of algorithm or whatnot. Yes, go ahead.
I'm sorry, this is a little off topic, but this, what we're covering right now, won't be on the test on Tuesday.
It will not on the test on next Tuesday.
Perfect. Okay.
Yep.
Thanks.
For your Wednesday's lecture, you did this already?
No, the Wednesday lecture is 1 day behind us, so they are going to get this on Monday. So yes, I know what you're thinking because you can watch the video on Monday, because it will have the full discussion. But that's based on the assumption that I remember to turn on the recorder on Monday. See, I'm skeptical. I'm skeptical of my own skepticism.
She got like a little reminder, like notification, turn on.
That would be very helpful, but I turn off all the notifications, because I'm in class. Yep. Go ahead.
Why don't you just like set like an alarm on your phone so that way when it vibrates, you can just look at what you.
Right. So I have to remember whether alarms, I have to allow exceptions because I think alarms are turned off too, during a silence, period, but you can configure whether it is allowed to go through or not. Yep.
We'll just tell you. We'll tell you from now on.
I think that would be great.
Is your thing will light up when you're recording? Or?
No, that's just, telling me that there's a connection between this and the USB dongle. But whether, the software is recording or not, there's no visual indication unless I look at OBS. But it's okay. I mean, you can probably just go to YouTube and find something. Oh, guess what? You just find out, relatively speaking, what is today's day number from the beginning of a semester. Go back one semester and look at how I taught this class last semester, right? Or the semester before that, or the semester before that, or the semester before that. You can listen to all, 8 different ways of explaining the same thing.
I think it gold left like 2009
2010 was the year that I registered the website with YouTube, but I did not have the necessary, okay, there were 2 things missing at that time. I did not have this wireless mic, so the audio tends to fade in and fade out depending on where I am in the classroom. And I also did not have the ability to upload more than 15 minutes worth of video clip at a time, because when you first register, they give you a limitation. You cannot upload like long video clips. So I wrote a program to chop my 80-minute recording into like chunks, and it will upload all the individual chunks, and I make playlists for each class. So even though some part of it is automated, it's still a hassle. But now it's just uploading the entire thing. Yep.
Okay, so since we have 11 bits that are used for the exponent,
Yes.
can we no longer just subtract doubles from each other in a subtractor and get?
You're correct. Yeah, subtraction is actually a bit of a problem, because it is just like, with base 10. If I say, this is 1.23E45, okay, and the next number is 23E67, and I want you to add those 2 numbers, the first thing you need to do is to align the decimal point, right? And it's the same thing here. Yeah, adding and subtracting floating point numbers is a pretty significant hassle. Okay, now that we are back here, we can look at this part now. So once again, V of something is just the value of the bit pattern. So F is just a bit pattern, okay? F does not really inherently have a particular value. It's just a whole bunch of bits. So V of F is saying, okay, what is the value represented by these 64 bits? Okay, the sign bit, is noted here. So, we'll call this the sign bit, S. So this is a ternary operator. If the sign bit is non-zero, then we return -1. If the sign bit is if the sign bit is false or 0, we return 1. Okay. If you're not familiar with the ternary operator, it's a good time to review what it means and how to use it, because I do use the ternary operator quite often, I guess, for the rest of this class. It's kind of like an if then else, but in a statement. I mean, in an expression. If this, then that, else that. That's what it means. Okay, so your C and C++ class really should have gone over the ternary operator, even if it does not go over some of the bitwise operators. The ternary operator is really, really helpful in programming. Okay, so this part really just takes care of the sign. Okay, are we multiplying the rest with 1, or are we multiplying the rest with -1? That's all it's saying. Is that okay? All right. But remember, if you're not familiar, or if you cannot remember how to use the ternary operator, try to do your own review of the ternary operator and learn how to use it. Okay? But in short, it is a conditional statement in an expression. The first one is a condition, second one is a then value, the last one is the else value. Are we good so far? Okay? So here's M2, which is this expression, and here's E2, which is 2 to the power of E2, and E2 is this guy here, and then E itself is over here. Is that okay? So you can see how M2 is just the mantissa. All it does is to say, this is a number between 1 and 2 excluding 2, but I can specify this value with very high precision because I have 52 bits to specify that value. Is that okay? I can specify values that are very, very, very close to each other and still be able to differentiate which one is which one. That's the really cool part of M2. E2, on the other hand, well, it goes from -1023 to +1024. Doesn't sound like a very large range, but because it is specifying the exponent of 2, we will still be able to specify a huge range of magnitude as a result. Is that okay? The sign bit, I mean, not much to say about that one. All it does is to say, is this value positive or is this value negative? That's all it's going to say. So are we good with this representation up to this point? Okay. So now we can use an example. Okay. So for the example part, so this is the part that if I do not record, it will be painful. Because the other part, you can kind of go back, and watch, videos on YouTube, right? You can. I mean, YouTube is a great resource when it comes to, finding, stuff like this. So search for IEEE double precision floating point number. Oh, double precision floating point. And there's a whole bunch of videos to help you figure out how to interpret it. Computer file is actually particularly cool. Okay, I have watched some of their other videos, not this particular one, and they usually do a pretty good job explaining concepts. Okay, so yes, so you got like a ton of ways to understand what a double is. But the example we are going to go through is going to be something, it's kind of, you can watch the other explanations too, but this is how I would explain it. So we'll look at a double with the following bit pattern. Okay, I'm just going to be randomly punching a bunch of zeros and ones. Okay, so 1, and then we have, let's see, 3, 4, 5, 6, 7, 8. Okay, and the rest are all zeros. Okay, so we look at this particular bit pattern and we say, okay, which one is bit 63? This is bit 63. Which one is bit 0? This is bit 0. Okay, so we need to make sure that we get the right orientation. Everything to the left-hand side are the more significant digits, to the right-hand side are the less significant digits. But this we have been using like for some time already, so I'm hoping that you guys already understand this convention. Is that okay? So now we'll try to chop up the bits and say, okay, what is my S bit or sign bit? My sign bit is bit 63 and the value is 1. Okay. What about my E? I just want the binary representation for now. So we look at the 11 bits next to the sign bit and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, this is our E as a base 2 number. Okay, we'll deal with E2 and the bias later on, because for now we just want to know, what are those individual things. So m, or the fractional part of the mantissa, would be the rest, right? So we count 11 bits from the all the way to the left hand side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So from here on, these are my mantissa, fractional mantissa bits. Okay. Okay. Do we have any questions of how I got each individual part? The sign bit, the e, which is not exactly the exponent of 2, but that's where we start, okay? And also the fractional part of the mantissa in base 2. So do we know how to chop it up? Yes? Okay. So now we take a closer look at e and go like, what exactly is that? Okay, this is in base 2. So if I want to convert into base 10, what is it going to look like? Well, I actually cheated because I chose a number that has a whole bunch of zeros. Because I don't want to add a whole bunch of powers of 2. We got 1 plus 2, right? A whole bunch of zeros. This is the last one. This is an 11-bit number. So bit 10, which is this one here, is represented the quantity of 2 to the power of 1024. So when you look at this entire thing, it would be 1027, because it's 1024 plus 2 plus 1. Are we good so far? Okay. Now, once again, I can do this math in my head, because I've been working with binary numbers for a long time. So I'm not expecting you guys to be able to instantly know the answer, given the bit pattern. But once I explain, oh, this is 1024 plus 2 plus 1, you really should know why it is 1024 plus 2 plus 1. Okay? All right, so if this is E, what is E2? Well, by definition, E2 is just E minus 1023 in base 10. So I guess it's just 4 this time. Is that okay? Yes?
Just to confirm, we figure out E2 in base 10, right? Not in base 2.
Well, this is the value of E2.
Yeah, I like the value.
Yeah,
Okay.
yeah. We want to know what value E2 is. So you can say this is 100 in base 2, which is the same value. But since we are all used to base 10 when it comes to doing calculations, that's why I write down the base 10 representation. Okay. All right. So what is M2 then? M2 is let's see what we can do about this. Okay, this is so M2 is 1 plus. That's mandatory, right? Do we have any halves? Okay, the half is going to be this bit. We don't have a half. Do we have a quarter? Yep, we got a quarter. Do we have an eighth? Yep. And then we don't have any 16th, but we have 1/32, right? So I'll just write 1/32 here. And then we don't have a 64th, we don't have a 128th, we don't have a 256th, but we do have 1/52nd, 1/12th, and we have 1024th, okay? And the rest are all zeros. Is that okay? Because M2, okay, so let me, I skipped one step, but if I don't skip that step, M2 would be 1 plus 0 point, and then I just take this bunch of stuff, copy, and paste. Is that okay?
So wait, it doesn't go to 1 plus 0.5?
So 0.5 is this digit. We have 0 of the 0.5.
Oh, in this example.
Yeah. And remember, this is base 2. So this bunch of zeros and ones, they're specifying the presence or the absence of a power of 2. But even though all of these are negative powers of 2, but nonetheless, they are powers of 2. So we have no half, 1/4, 1/8, no 16th, 1/32, and blah, 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 blah. Is that okay? So can we know the value now? I think so. Okay. So using all of this stuff here, we now say the value of this particular floating point number is the sign bit, question mark, negative 1, 1, times m2 times 2 to the power of e2, okay? That's the definition. So now we end up with negative 1 because the sign is a 1, so we have to choose the then value of the ternary operator. M2 is this bunch, so I'm just going to copy and paste here. Because the actual calculation is not really, it can be done with a calculator. That part I'm not concerned about. And then times 2 to the power of what? 4. There we go. And if you prefer, we can rewrite this entire thing just a little bit more legibly. Okay, that's 16. Or you can take that 16 and combine that with a minus 1. Okay, kind of the same thing. Is that okay? So we can actually input this into a calculator and find out exactly what it is. Okay, so let's do that. I'll just try to do this as quickly as possible, which means I'm going to use a spreadsheet to do it. This is from my other class. It's okay. We'll just kind of copy this and paste it over here. So the idea is all those bits, okay, all those zeros and ones, interpreted as a double is actually representing negative 22 point blah, 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 blah. Is that okay? Now, knowing me, okay, I don't trust myself. Neither should you. But you should trust me not trusting myself. That part you can count on. So what is next? What is the next step? What am I suggesting? What am I foreshadowing, as they say in English writing? Let's check it, right? So how do we check something like this? Is there an online calculator that can do this? Maybe, okay? But we don't need that, okay? So what we're going to do is to have some fun with GCC and GDB. GCC is what you normally know as the C compiler, okay? I'm going to write a very small program that can help me with this, okay? I don't think you have to copy this because it's really, really simple. So I'll just write this program as test, okay? Test.c, pound include stdint.h, okay? Standard integer.h. This allows me to specify the width of integers. We have int main, and inside main we're going to have let's see, uint64 underscore t, and we'll just call this u. Okay, so u as a variable is nothing more than just a 64-bit integer. Okay, no big deal. You get 0 because without that, the compiler would actually optimize the variable out, and then that defeats the whole purpose of having this program. And that's it. This is my entire program. And then you go like, but this program doesn't even have a single double in it. So how is this going to help us double check whether the bit representation is correct or not? Well, that's the job of GDB. Okay, so here's my program. Let's compile that with a -g to include debug information. Warn all, so that if I do something stupid, the compiler will say, "Tag, you just did something stupid," which is good. Because it's better for the compiler to find out that I did something stupid than to have runtime error later on. So it does complain about something. It's a warning. It's not an error, which means the program did compile. I have an executable. What it's complaining about is variable u is set, which means there's an assignment statement where u is on the left-hand side. But after that, the value of u is not utilized anywhere in the program. Okay, so it's just a warning and say that, hey, you got a variable here, it got a value, but you never used it. Okay, so it's a valid warning in all other situations, but in this case, that's the intent of the program. So I'm gonna say, okay, this is fine, don't worry about it. Then I use GDB. Okay, GDB is the debugger, that is behind code blocks and many other GUI type IDE for C and C++. So I GDB test, which is my program, list the program, put a breakpoint on line. I don't even care which line I put a breakpoint on. I can put a breakpoint on line 7, okay? And I can run the program now, okay? And I can single step, print u has a value of 0. We're pretty good so far. Yes? Okay. So the next thing I need to do is to put the 64-bit pattern of the double that we just figured out into u, into the variable u. Is that okay? How should we do that? Okay, so let's check out Notepad first. So I'm talking about turning this into a value that, and then put it into variable u. Okay, so how do we do that? Well, this is where base 16 comes in very handy, because this is a pretty long number. It has got 64 zeros and ones. But when you look at it from the hexadecimal perspective, it has only 16 digits, which is still a lot, but not nearly as much as otherwise that I have to deal with. So when you convert from base 2 to base 16, you chop it into chunks of 4 bits. Okay? Actually, 4-bit is also called a nibble. A byte is bigger than a nibble. And then the bit is smaller than a nibble. You see where that goes? Yep, that's computer science people for you. A bunch of INTPs, because INTPs tend to play with words like that. Okay, so this is a C, this is a 0, this is a 3, this is a 6, this is an 8, that is a C again, and a bunch of zeros, okay? So the only part I have to know is how many zeros we are talking about. We got 6 digits, so we need 10 zeros to make up for 16 digits, okay? So let's switch back to GDB, and I say set variable u to the following hexadecimal representation. And of course, I cannot remember exactly what I said earlier. There you go. C0368C, and then 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Press the enter key. Print u again. Wow, that is not negative 22 something, okay? Maybe if I specify hexadecimal, that would give me something. Nope, that just gave back the original hexadecimal representation. What about printing it as a --t? This is the only thing you can do in, one of the things you can do in GDB, but not in C and C++, is to display something in binary instead of hexadecimal, octal, or decimal. Okay, so /t is binary, and it gave us back a whole bunch of zeros and ones. Well, maybe it's a good time to double check, right? So we'll double check, are we getting back the original bit pattern? 1100, 0000, 0011, 0110, 1000, 1100, and a whole bunch of zeros after that. Okay, so we just double checked that the 64-bit, the bit pattern itself, is now in variable u. Okay, so, but if we interpret it as a double, are we going to get back negative 22 and something? That's the next question, right? So most people would say, oh, we can just cast it then. We can cast u into a double. That is not going to work. Oh, spelling mistake?
That's definitely not gonna work.
Right, for the wrong reason though. Okay, so double. Okay, so print w is, oh, w, that's funny. So yeah, this would be bad for people who cannot see what is on the screen and only hear what I say. Print w is not going to work. Yep. So print in parentheses double, then u is not going to work, because what this is doing is it's taking It's looking at the value of u first, which is this huge number that we saw, okay? And then it will convert that into a double representation, which means we are still going to get back this particular value, but it'll be represented a little bit differently using scientific notation. Okay, let me press the enter key and we can see exactly that. Yes? So see, we got like 19 digits of significant digits for a huge, long 64-bit number, right? We kind of knew that from earlier discussion, but we are not getting negative 22 point something. The reason why that is the case is typecasting in this case is already interpreting u as an unsigned 64-bit integer. That is the value being converted into a double. So it's not really saying, okay, don't look at these zeros and ones as an unsigned, look at it instead as a double. That is what we want to do, but a simple cast doesn't do that. Okay, so what can we do about that? So let's say we say print. Okay, so I'm going to construct this step by step, so don't copy because I'm going to go back and forth and change a lot of things. Okay, that is just u itself. Okay, we already know if we say print u, we get $2 back. When I say $2, I'm referring to this $2, which is a previous result of a print. Okay, okay, that's not helpful. Okay, what about this? What is %u? This is C syntax. Go ahead. The address of u as a variable, okay? Okay, so it will give us an address. Not going to be very helpful. What is the type of this %u? I don't really care about what it's going to print because it's just some location in memory. But what is the type of %u? No. The type is unsigned uint64_t asterisk. It is a pointer to a 64-bit integer. Is that okay? You can also look at it as the address of a 64-bit unsigned integer. We good so far? So when you look at the type of this, okay, it is an address of a 64-bit integer. The key is it is an address of something. Is that okay? Can you typecast? Yes, go ahead.
What types are addresses?
You can either call them pointers to or the address of the other type. So in this case, it would be the address of a 64-bit unsigned integer. Can we cast pointers in C and C++?
Does that one cast the pointer itself? Or is it
I'm casting a pointer of one type to a pointer to another type.
I think so.
That is the whole idea of C and C++. That actually is also part of why I describe C as a circular saw, which is basically just an electric motor, with a blade welded to the axle. Because when you cast pointers, C and C++ does not check whether it makes sense or not when you do that cast. It simply says, oh, this was the address of an unsigned 64-bit integer, but if you want me to look at this as the address of something else, sure, not a problem. I can totally do that. That is what C is doing, okay? And as you can probably imagine, that can lead to all kinds of problems if you are not careful with the casting of pointers, okay? And that circular saw has no on-off switch, has no guard, has no safety features whatsoever. That's the tool that you have been working with and will work with for a long time. Okay, so I can cast this. So what I'm going to cast this to is this. Now, this is the tricky part. This is the best part of this whole demonstration. I take a variable that is sitting in memory. How long is a 64-bit unsigned integer? How many bytes is it going to take? 64 divided by 8 is 8 bytes. Very good. How big is a double? A double has 64 bits, so it also has 8 bytes, right? So now I look at the 8 bytes that was originally used as an unsigned 64-bit integer, and I'm telling GDB and go like, just change the way you look at these 8 bytes. Okay, look at this as 8 bytes of a double. So it is reinterpreting the 64 bits contained in those 8 bytes now as a double, not as an unsigned integer anymore. In other words, it's all about the interpretation of the bits. It's the same bits, but the interpretation is now different. Is that okay? Yep, go ahead.
Does reinterpret cast do about the same thing then?
Say that one more time.
Does reinterpret cast do about the same thing then?
Reinterpret cast.
Yeah, I remember it being a function. It's been a while since I've used it, so I don't know exactly how it.
Are you talking about taking in parameters, you're only using void pointers, but inside the function you convert the void pointers back to what it is supposed to be? Is this from Professor Fox's class about encapsulation of types?
I think so. We were basically working with binary files at the time.
Binary files. Okay. Yes. So it's doing the same thing as that. Okay. But I'm not really sure which class would do that. Is it a class from Fox?
It was Fox, yeah.
Oh, okay. Yeah. So it is. I'm using the same trick basically.
Oh, okay.
Yep. So I'm reinterpreting those. Okay. But if I press the enter key right now, what do you think it's going to print? It's going to print the address because I'm still talking about the address of you. I'm just saying instead of looking at this as an address of a 64-bit unsigned integer, look at this as an address of a double. Okay, so I can give you a quick analogy. Okay, let's say you have a street address in a normal residential neighborhood. Okay, so it is blah 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 so and so street and whatnot, and normally it is a residential address. Okay, casting an address is basically saying do not look at this address as a residential address anymore. Consider this as a commercial address. Okay, because there are certain things you can do with a residential address, but not as a commercial address, and there are certain things you can do with a commercial address, but not as a residential address. Okay, so it might have to do with like, can FedEx drop off a pallet, okay, a huge big item, at this address? Might have something to do with that. May have something to do with, can UPS pick up at a particular time of the day from this address? Is that okay? So I'm just casting the address, but I'm not doing anything with the address at this point. I'm just saying, well, this is actually a residential address, but cast it into a commercial address. So now I can do whatever I can do with a commercial address. Is that okay? So now I take this whole thing, okay, and say, let's dereference. What is it dereferencing? Well, tech, it seems like you're just doing a whole bunch of nonsense, and we get back to whatever we started off with. You take the address of, and then you dereference that thing, you get back whatever you got. But wait, it is not interpreting those 8 bytes as a unsigned 64-bit integer anymore. Because what we're dereferencing is now the address of a double. It's looking at those same 8 bytes with the same 64 bits, but now it's seen as a double, not as an unsigned 64-bit integer anymore. In other words, it is no longer looking at bit 62 as a part of the value. It is now looking at bit 62 as part of the most significant, as the most significant bit of E. It's looking at bit 0 to bit 51 as the fractional part of the mantissa, and not really as just the plain power of 2 that we are supposed to add. Is that okay? Does everybody understand what I mean by interpretation of the bits? Okay, very good. If not, I will give you one analogy, and that's the end of it, okay? What is this? So I just gave you a bunch of bits, okay? I'm asking for your interpretation now, right? It depends on what class we are in. In a math class, this is probably reasonable to assume this is a line segment in a math class, right? In a Chinese class, This is the character representing 1. In an English class, this is probably a hyphen or one of those other punctuations, because there are longer ones and shorter ones, but it's probably a punctuation in an English class. So is that okay? So in an English class, okay, for instance, in an English class, I write this on the chalkboard or the whiteboard, and I say, okay, forget that you're in an English class. Pretend that you're in a Chinese class. This actually means 1 now. I'm changing the interpretation of something. Is that okay? That's exactly what we are doing here. Press the Enter key, and guess what we got? What we wanted to see. So this little exercise not only illustrates that our interpretation of these bits, it not only illustrates how to look at the bit pattern inside a 64-bit double precision floating point number, but it also kind of illustrates concepts that you may or may not know in C and C++. I think the one part that you may not be familiar with is the casting of pointers. No, that was discussed. Okay, it should be discussed already, but this is one weird way to apply the casting of pointers to kind of say, okay, let's look at this as blah blah blah. Yep.
Could you explain again why just doing like casting double to U wouldn't work? Like how would that look in the example that you just showed?
Okay, so you're referring to this part here, right? So $5 does not work because from the compiler's perspective or from GDB's perspective, it is first saying, okay, you want U, okay? But when you when you specify U as a variable name, are you referring to the address or are you referring to the value? The value, right? So I'm taking the value of U, which is this huge number here, okay? So you're taking this huge value, which is next to $2, and you say, okay, represent the same thing as a double. Sure, I can represent the same thing as a double, but when it prints it out in base 10, it looks about the same, okay, because you're just changing, it's now a scientific notation, but you get most of it back, except for the last 4 digits. They're all rounded into just a single 8. Is that okay? All right. So I don't have enough time to go the other way around. Okay, let me tell you what I mean by the other way around. This is something that you can do. I know you have to study for the exam on Tuesday, okay? But if you do have some spare time, I want you to think about this. Because I'm doing just the reverse. What if I do something like that? Okay, I say, okay, this is 6, which is just a normal integer 6, okay? I'm going to store 6 as a double into the place where we normally interpret as a 64-bit integer. Okay, so if I press the Enter key, it won't give me an error. Okay, so now the 64-bit of variable U will now be the double representation of 6. Now you might say, what, isn't 6 just 110 and with a whole bunch of zeros to the left-hand side? Not anymore. Okay, because now 6 is represented using a sign bit as bit 63. It has an exponent as bit 52 to bit 62, and it has a fractional mantissa from bit 0 to bit 51. And we look at those components the same way that we did, with all of these things. So the bit pattern representing the value of 6 as a double is now a bit more complicated. Okay, so if you have time, I want you to do an experiment like this. Okay, try to figure out what bit pattern you think should be printed when you say, okay, I'm not going to press the Enter key because that would give you the answer, and I don't want to give you the answer. I mean, obviously you can just kind of do this and replicate the whole thing and get the answer. But I want you to think about what this command is going to do, what is it going to print? Because this, if you can successfully do this step here, it means that you understand the conversion process. Okay, and just trying to go through that process can help you get a deeper understanding of what is a double representation. So we can go over this next Wednesday, no, next Thursday, a week from today. And because this is all getting recorded, I can just kind of back up and redo this part, and then go forward and say, okay, how do we know what is going to be in U, when we go through this process? But having you at least to go through the process, maybe after Tuesday and before Thursday next week, is going to help you understand all of these concepts. We do have a lab today for double representation. So we're going to go to the lab, and you can get started with this one. It is not due until next Thursday, just like it has 1 week of time for you to work on it. So if you say, oh, I really need to study for Tuesday's exam, I understand, okay? But the earlier you can get this out of the way, I think the better it is.